Hello everyone, my name is Leo. This is the supplemental video for UCSC Professor Munishkina CSE30, Programming Abstractions, Python, Notebook Assignment 3, Recursion and Generators. The purpose of this notebook is to provide you with knowledge of implementing recursive functions and generators. In this notebook, you will practice with creating generators for Fibonacci numbers, prime numbers, permutation, combinations, and power sets using recursive functions. So let's firstly see what recursion is. Recursion is a process of executing the same function multiple times by calling the function from inside of itself. All recursive functions should have three main components. The first one is base case, which is the simplest case among multiple possible situations. The second one is recursive call, which is where the function calls itself inside itself. And the third one is decrementing or dividing the task into subtasks, which means the recursive function calls has to approach the base case. Therefore, we can touch the base case gradually by calling it over and over again. The last thing is not necessarily a component, but it's more my personal understanding to figure out how a recursive function works more quickly. It is always assume that recursive call in the function solves the problems for you, which we will cover later in the generator section. Now let's see a real recursive function. Say that we are printing hello n times, and this can be easily done with a for or while loop. For example, for I in range n, and we just print hello and we can print hello n times. However, most programming problems that can be solved using a loop can also be solved using recursions. So in this case, as we mentioned earlier, one of the three components is base case, which is the simplest case. In this scenario, it will be n equals to 1. So we say if n equals to 1, then we just print hello once. Then it will be in other cases where we implement our recursive calls. So we can print hello once, else print hello, and then call the function again to print more hellos. However, since we already printed once here above, in a recursive call, we will decrease the parameter n by 1, indicating that we only need n minus 1 hellos this time, and we're done. Also, we can get rid of the return or add a return here. It does not matter in this case because this if-else statement is the only part of the function. Now, say if we call hello3, the function goes to the else branch. Since n equals to 3, which is greater than 1, then we print hello. So it will look like this. Print hello. And it goes to the hello n minus 1. It calls the function itself again. And in the recursive call, we go to the else branch again, since in this case, n equals to n minus 1 equals to 2, which is also not 1. So what I'm saying is we are going to hello 2, and in hello 2, we go to the else branch again, and we print the hello. After printing hello, we are calling the hello function again, and in this layer, it will be hello 1. So as you can see, we are touching the base case gradually by calling it over and over again. And when we call hello 1, the parameter n equals to 1, and what we are doing is only printing a hello. Now we can see we print 3 hellos in total after calling this function, and this is how the recursive function works. Furthermore, we can switch the two call lines in the else branch. We can call the hello function first, then print the hello. And let's use the hello3 as an example again, and we can see it will actually turn into the same result. In this case, it will be go to the else branch, call hello minus 1 first, which is hello 2. And then because we are calling hello too, so we are returning to this function, and since in this case the parameter n equals to 2, which is not 1, then we call hello n minus 1 again into another layer, which is hello 2 minus 1, which is 1. And now we are going back to the function again, and in this case, since n equals to 1, so we are just printing a hello in the ones inside. And after printing this hello, we're going back to the previous layer where we end calling this function and printing a hello again. It will be the same layer with the hello1 function. Print hello. And we can see we finished this, and we can just go back to another previous layer, which is the same layer of the hello2. And we can see after calling the hello function, we're just printing another hello. We can run the cell. We have 3 hellos. And this can also be seen here in our pseudocode. After seeing the recursion, we can discuss where it can be used in real life. In mathematics, we can use recursion to do proofs by induction, to define mathematical sets like Matterport set, or to define sequences like Fibonacci numbers. We can also write a function to generate the first n terms of the sequence, which we will cover later. In computer science, we can use recursion in substituting iteration like factorial function, defining recursive data types like linked list and trees. We can also use it in implementing divide and conquer algorithms, since as we mentioned earlier, the third component of a recursive function, which is also the essence of recursion, is decrementing or dividing the tasks into subtasks. We can use it to implement merge sort, quicksort, binary search, etc. We can also do dynamic programming like Fibonacci memorization and functional programming. The easiest case will be sum of a list. We can also do backtracking like Sudoku solver, which will involve trying out potential solutions and backtracking if a solution leads to a dead end. In the future, we will also use recursion to do tree and graph traversal, involving BFS, breadth first search, and DFS, depth first search. We just simply mentioned these concepts here, but we are going to talk about most of them in later notebook videos. Now let's see another example, printing numbers recursively. Say that we are writing a function with a parameter n that prints integers from 1 to n chronologically. Similarly, we can do this easily with an iteration. For I in range 1 to n plus 1, then print I, and if we run the function with the parameter 10, we'll see integers from 1 to 10. Furthermore, we can do this with a recursion. Similar to the function we worked on earlier, the base case for this function will be n equals to 1. Then we're just printing all integers from 1 to 1, which will only be 1. Then it will be our recursive call. Else, since we are printing numbers chronologically, starting 1 up to n, we want to print the integer that is 1 less than n, which is n minus 1, before printing n. Then we can print the number n itself after that. So I can say print numbers n minus 1, and then print n itself. And then we return the function. And if we run the function with the parameter n equals to 10, we'll see integers from n 1 to 10. As I mentioned earlier in this video, the fourth component, or key to understanding a recursive function, is that we always assume that the recursive call will solve the problem for us. That is, will do what the function should do. And in this case, print numbers n minus 1 will do what we expect it to do, which is to print integers from 1 to n minus 1, because the function print numbers is to print the numbers from 1 to n. And if we change the parameter from n to n minus 1, it should do the same based on our assumption. And this is what I was trying to say earlier. We'll use this method later to understand more recursive function in this notebook as well. After understanding the recursive function, we can move on to generators and iterators. A generator is a function that has a yield statement. A yield statement works similar to a return statement, but the function state is not erased from memory, so the code after yield can be executed. Say our first function for, we have a variable equals to 0, and we increment it by 1 in each for loop. If we return the variable here, it will only execute the loop once and stop the function as soon as it touches the return command. As we can see here, it only returns one variable, which is 0, its initial value. However, if we used the yield statement here instead, and when we call the function again, we'll see it has turned into a generator object, which is an iterator with a function called next. We can use this next function to iterate through all the variables we yield earlier in sequence. Let's see an example here. I define iter fun equals to either my fun generator, and if I print next iter fun, it will return 0, since the first variable we yield is 0, and we could do this multiple times until we hit the end. Say if I do it 3 times, it will return me 0, 1, 2. However, if I do it 4 times, it will give me an error called stop iteration. The iteration stops here because we only yield 3 variables, as you can see here. We only have 3 for loops executed. Here is another example of a generator where we only have 2 yield statements. Here we define G1 equals to line generator, and we can see G1 is in generator class if we print type of G1. And if I call next, we can see it is giving us the value of the variable we yield in sequence. The first variable we yield is the first string, and the second one is the second string. And we are getting it in sequence. Also, if I add another next command, the iteration will stop since we are out of range. Now imagine we are using iterators to generate a mathematical sequence, and we want to write a function to generate as many numbers as the client wants, which means we will have infinite yield statements in our generator function. This means we are most likely to implement a loop here. Say that I want to generate powers of positive integer numbers. I can firstly define my power numbers generator. So we are starting with I equals to 1, since the power 0 of any positive integer will be 1. After yielding it in our while loop, we multiply the result by the integer k, so that we can add 1 to the power of the integer k, and we are done. We can get rid of this return statement, and now say that I want to print a sequence of powers of 2 that are less than the 1000. To do this, I can write a for loop to iterate over my generator in sequence. For n in power numbers, and what I want is the sequence of powers of 2. So k here should be equals to 2. And I say if n is greater than 1000, I want to break the loop, else I want to print the n. Similarly, if I want the sequence of powers of 3 that are greater than 100 and less than 1000, I can say for n in powers number 3, and if n is smaller than 100, I want to continue to skip it, and if n is greater 1000, I want to break the loop. Otherwise, we can print n. And if we run a cell, we can get the answer we want. As you can see here, we do not implement restrictions in our generators. What we say is just while true. But when we are actually using these generators as a client, we do have some limitations. Like if n is greater than 1000, we just break the loop and stop it. And if n is smaller than 100, we're just skipping it. Now, I want to briefly talk about question 1, Fibonacci numbers. There are different ways to implement a function to generate Fibonacci numbers. Firstly, we can do it through a loop. Say that we want to write a function printing the first n elements of the Fibonacci sequence. Here we can set the current equals to a equals to 0 and b equals to 1. The variable a here means the first element of the Fibonacci sequence, and b is the second element, as you can see here. The current here is more like a cursor, which points to the element we are going to print out. Next, we have a variable called count that helps us to keep track of the number of the elements we print out. And we can set it equal to 1. Then we can have a while loop here, while count is smaller or equal than n, and then we can print the current like the cursor, and we can move the cursor to b to the next level, which means we can move the cursor to here. Meanwhile, we can move the b to the next cursor as a plus 2b, and we can move a follow along the current cursor to make every single element updated. And lastly, we are updating the count by plussing 1. And if we call the function, let's say we are printing out the first 10 elements of the Fibonacci sequence, and this is what we get. This method can also be used in the Fibonacci generator function, which you will work on later in this notebook. The next method is using a recursive function. As we observed here, the first element of the Fibonacci sequence is 0, whose index is also 0, and the second element with the index of 1 is also 1. So we can say if the index n here is smaller or equal than 1, then we can just return n itself. Else, in other cases, based on the definition of the Fibonacci sequence, the element n should be the sum of the previous two elements. So we can return Fibonacci n-1 plus Fibonacci n-2. And then we have a for loop. For I in range 10, print Fibonacci I. We can see that we have the same output as the previous function. However, this method has an obvious drawback. Every time it calculates a Fibonacci number, it will actually start from the very beginning. Say here we want Fibonacci n-1. It will actually calculate Fibonacci n-2 and Fibonacci n-3, and so on until it hits the base case, where n is smaller or equal than 1. While here, when we want Fibonacci n-2 again, the function will recalculate everything following the same steps. Therefore, if we print, say, the first 100 elements of the sequence, it will actually take a dramatically long time. As you can see here, then we can have another method, Fibonacci with memory. This time, we have one more variable, a dictionary mem here, whose key value pairs are index and values of the Fibonacci sequence. Same as before, if n is smaller or equal than 1, we return n directly. Then we check if the index n is in mem or not. If yes, we can just return the value it corresponds to. Return mem n. If not, we just calculate it. But before returning it, we store it in the dictionary. Mem n equals to Fibonacci mem n-1 plus Fibonacci mem n-2. And we return it eventually. Therefore, we can just retrieve it next time when we want to use it. And if I run the function with the range 100, we can see it actually prints out everything really fast. And if we want to print a sequence here, we can see the dictionary actually contains every single key value pair of the Fibonacci sequence, which we retrieved during the function. This is the end of the video. Now your assignment is to complete the notebook exercises. Please read the instructions carefully before starting. Feel free to reach out to professors peers and tutors if you have any difficulties. I'll see you later. Thank you.